Let's talk about handling traffic spikes through automated prioritized load shedding. I'm Benjamin Fedorka. My pronouns are he, him, and I work on the Java platform team at Netflix. My main focus is helping engineers easily integrate their backend systems. We deliver a consistent developer experience for point-to-point communications in JVM applications. We do it by providing a variety of RPC frameworks, including Netflix gRPC Java, Netflix Web Client and REST Client, Spring Web MVC, and a bunch of related tooling like the Netflix Concurrency OSS library, Spring Boot integrations to make all of this easy, schema management, and ad hoc requests. Netflix gRPC Java is our most highly featured and complex RPC framework. We have over 600 applications serving 1,300 services and over 1,500 applications with gRPC clients. So it's critical that all of this is easy. We call making this easy our paved road. We approach this challenge from 5 angles: tooling, how do engineers author schemas and send ad hoc requests; security, how do we establish and enforce RPC integrity and access controls; resilience, how do we ensure that RPCs succeed or degrade successfully; observability, how do we make sure that the behavior of the system is easy to see and understand; and ergonomics, how to make all of this easy. This year, I'm continuing our transition of sharing details about what we've learned and where we've succeeded by diving into our capabilities for handling traffic spikes while protecting our customer experience. When our content team shared their plans for our 2024 and 2025 releases, I was really excited. I love our vision to entertain the world, and we had a lot of high-profile content. But when we set the goal to start surviving load spikes without increasing our server capacity, I was concerned, because this isn't just one problem. It's hundreds of similar problems. My team supports services across all aspects of the business, and every cluster's got a unique performance profile. We have years of experience helping teams operate our existing resilience capabilities, but our best tools either require hand-tuning each cluster or leaves a lot of performance on the table. We need to find more capacity in our existing clusters, and we need to make that process scale. So I'm going to talk about, first, the elephant in the room: why not just autoscale? I'm going to talk a little bit about our theory, how we think about service capacity and failure, how we started measuring server utilization, and then I'm going to shift into where our successes were, really leaning into prioritizing requests, de-sharding clusters, how we validated all these configurations, and I've got one slide that's going to help you understand how we've got it wired up and how you might be able to apply it. So easy, why not scale up, right? It's super easy to do. It's reactive. You start getting loaded. You just throw more servers at it. Why not just do this? And of course, the answer is we normally do, right? We do actually allow customers to auto-scale, and we pre-scale before content releases. So why doesn't that solve our problem? So scaling up has issues, right? First of all, it's costly, right? Adding our code to more servers, it's just going to be more cost, right? It doesn't matter if we have a cloud provider or running our own data centers. We're going to use resources that we might not actually have. 2, we hit capacity limits, right? We might reach the number of nodes that we can't actually add anymore. We can't operate more nodes. Maybe we have a control plane that gets maxed out, or maybe a database can't take any more connections. Scaling is also not always fast. If we underscale a cluster and we have to let it autoscale, it actually takes time to get the new instances started. Once they're started, they're likely to come up cold, and they're going to have worse performance for the first couple of minutes. This makes it less reactive because maybe all your users hit the home page at once. You're going to get a different load profile than you pre-scaled for, and you might not have the capacity to make that successful. Through our work, we did expand on our techniques for both pre-scaling and autoscaling, but we didn't actually rely on them to meet our goals. So let's go back to the basics. If we don't do anything, what's the most common way for our systems to fail during a load spike? So this graph is showing a system getting an ever-increasing amount of traffic. The green bars are your successful requests. The red bars are the ones that fail. As the total number of requests continues to increase, so does the system utilization. Unfortunately, the system reaches a tipping point where the utilization goes 100% and almost all the requests are failing. This is the worst case scenario. We call this a congested failure. So why is this so bad? This system can rapidly transition from successfully working to failing. If it had continued serving successful requests while failing some others, there would be more of an opportunity to implement a graceful degradation. Even worse, the system never recovers. The system failed to serve almost all requests for 10 minutes with no indication of getting better. Even if we detected this and restarted the node, we'd have to pay the cost of the restart, and then you have that cold node again. So we need a better solution. So let's think about our system like a highway. Most of the time, there's plenty of room for all of the traffic. In fact, there's even capacity for small spikes. We call reserving this capacity our success buffer. We can successfully serve additional requests without any failures. If you've ever intentionally run a system cold, you create a success buffer. Now, if we get too much traffic, there's a big traffic jam, nobody gets home. This is what we call congestive failure. So let's start with an easy fix. We put a stoplight on the on-ramp, and we only allow cars when there's capacity. We call this a failure buffer. We reserve some capacity for gracefully rejecting requests without suffering from the congestive failure. The requests which are blocked can be shed, which means that they'll never be served. However, some requests are still getting through, and we know which requests have been shed, so we can respond gracefully. So to operate this stoplight, we need to know how many requests can your system support. Well, it depends on a lot of things. How many requests can a single node support? How many nodes are there? Are all the requests similar in cost? Are some more expensive? How does that request mix change over time? If you call another system, how many requests can that system support? We used to try to answer all these questions and come up with a number for each cluster. That process is time intensive, and the results had dubious quality as those numbers change. Instead, we decided to measure a small number of concrete signals. We can objectively measure things like how much CPU is being consumed on the node, are any of the resources experiencing queuing, and what is the utilization of supporting services. But the most important one that we matters is how long does it take to measure each request. When you think about it, in the highway analogy, that's what we really need. How long did it take for you to get home? The challenge is we need to understand how long it normally takes for each request, and they're all different. We need to automatically distinguish between the unique types of work the system performs, and if that work is conforming to an expected latency distribution. We used to track latency distributions on a service level, but we now track it for each individual RPC. This helps us better accommodate a changing request mix throughout the day. Each server in the cluster is continuously analyzing its own performance, normalizes that raw data into a value, which is going to represent your system utilization. When the system utilization gets too high, we reject requests. Now, these techniques aren't new, and we refined them over the years. 12 years ago, we published a blog post introducing our techniques for load shedding. And 7 years ago, we introduced a blog post with our improvements to those techniques. We open sourced these via the Netflix concurrency library, and that implementation was used as a reference as they spread to other projects like Envoy. We're standing on the shoulders of giants, but it still didn't give us the capacity we needed. So far, we assume that all the requests should have equal probability of being rejected. But not all requests have the same value, and we can leverage that to our advantage. When you go to netflix.com, the website can predict what you're going to click on and prefetch that information. This will help you start that next episode of Wednesday a little bit faster. It's okay for those projections to be wrong. You'll still be able to watch Stranger Things. But once you click on Stranger Things, we need that data as soon as possible. That request is now critical. And this is the key. We didn't really need to increase the success buffer for all requests. We only need to increase it for our most critical requests. So we upgraded our traffic light. We wanted it to be priority aware. When there's no congestion, we want to serve all of these pre-fresh and non-critical requests. They'll help us deliver that better experience. But if load is increasing faster than we can scale, we progressively block requests according to their priority. During periods of very high congestion, we might even block important traffic while still allowing the most critical traffic through. Previously, we applied this logic at the edge, but we now have the capability to apply this at all layers of a stack. This allows us to be more responsive to unexpected load patterns and to issues occurring deep within the call graph, so we can degrade specific capabilities instead of just the user experience at the edge. So here's an example of how we might start shedding load. The request priorities are simplified here into 4 buckets. So during periods of very low use, we're going to accept all types of requests. As the utilization begins to increase, we drop lower priority requests. We do this gradually so the other systems have a chance to adjust to these changes. If that utilization becomes very high, we're even going to start shedding critical requests because we'd rather serve some critical traffic than none, and we'd rather serve no critical traffic than risk the system crashing and requiring a reboot. We tune these thresholds for each cluster so we can customize the throttling response for each expected request distribution. This gave us half of the solution. So a few years ago, we would shard our traffic by criticality. Both success and failure buffers implemented by having unused capacity, and that's expensive. We could save money by allowing the non-critical requests to have less buffer. We could also optimize a shard for throughput instead of latency, which is going to reduce our cost for batch traffic. If we were to de-shard this traffic, we now have all that capacity available for critical traffic. This substantially increases our success buffer for critical calls. And we might even be able to use less overall capacity because we're now more efficiently using our resources to serve that non-critical traffic. Even better, we're also operating fewer clusters, which is less cognitive load on our engineers. Now, we don't need to deshard all services, but this technique is a great way to increase the success buffer for your most critical traffic. We have immediate access to our additional compute resources when we need it, while we're still efficiently using them during normal load. So combined, these techniques gave us the access capacity we needed to find. We refined our existing load shedding capabilities to maintain specific success and failure buffers. We realized we didn't need additional capacity to serve all requests. We only needed that capacity to serve the most critical requests. And we were able to deshard clusters to create additional success buffer for the most critical traffic. By shedding lower priority requests, we can give that capacity to the high priority requests. By automating this decision, we can have it respond faster than the fastest 3. And by applying this capability on a per cluster basis, we can allow capabilities to gracefully degrade while the rest will operate at their maximum capacity. So let's compare this behavior to the system suffering from congestive failure. The system with prioritized load shedding doesn't tip over and fall. It's always serving that baseline set of traffic throughout the load spike. Early in the spike, the system shifts to only serve critical traffic, ensuring that we're providing the most value with the requests that are served. Now, eventually, we're not going to be able to shed load fast enough. We still define target failure buffers, which is the percentage of RPS we need to be able to shed before impacting successful requests. If the load goes above our failure buffer, the server will still reject those requests, but might serve fewer successful requests as a result. So routing more traffic to fewer clusters is a straightforward operational shift. So let's focus on how we rolled out the prioritized load shedding mechanism. So the system requires a lot of tuning. We need information about the expected latency distribution for every RPC. We need information about the expected request priority distribution for every cluster. We need information about the expected utilization levels for CPU and data stores for every single cluster. This is too much to maintain by hand, but that's not really a problem for platform engineering. So we designed and built a system to manage and validate our load shedding on a per cluster basis. So the system automatically generates a proposed load shedding and autoscaling configuration, automatically tests the configuration with an experiment, automatically validates the outputs of those tests, and automatically applies the configuration to the production clusters. The first step is an automated analysis of each cluster during normal operation. We integrate signals such as historical call latencies, call volumes, request priorities, CPU usage, and a little bit of expert advice to generate a resilience configuration. This configuration includes the information we need to track if the CPU is within expected range, if requests are completing within the expected latency distributions, and the priorities of the requests that we expect to serve. Exactly what we need to make load shedding decisions. I mentioned that our work on prioritized load shedding also improved our scaling, and you can find that information in the resilience configuration. We also have the information we need to quickly detect load spikes and to predict how many resources we need to serve that traffic. If that capacity is available, we can scale up automatically and satisfy a dual goal. Clusters should survive load spikes while continuing to serve the baseline traffic, and clusters should quickly adapt to serve the traffic spike when there's capacity available. Each resilience configuration is validated through our experiment automation platform. This experiment applies the candidate resilience configuration to each cluster and validates that it's correctly serving the baseline load. Once that cluster is validated, we intentionally route a traffic spike to the experiment cluster. We confirm the cluster has the expected success and failure buffers, specifically that it's gracefully rejecting traffic while considering to serve that baseline load. The charts on the slide show a great example of a successful test. After the cluster warms up, we see a traffic spike and the server briefly throttles. 3 more servers are started, and within 2 minutes of the spike starting, we're successfully serving all traffic. Our automation not only orchestrated this test, analyzed the results, it promoted its configuration to prod. From a technical standpoint, load shedding capability is primarily implemented through a relatively simple gRPC interceptors and envoy filters. A gRPC client interceptor annotates outgoing requests with their priority. This priority is propagated to all requests through the call stack. To learn more about how we handle metadata like request priority, managing contextual metadata across the gRPC ecosystem is being presented by my colleague Nicholas Hagen in Western Sycamore right after this talk. A load shedding decision is made in a proxy sidecar, Envoy, using the request priority set by the client. For the requests which are allowed, a gRPC service interceptor is monitoring the latency distribution and compares that against the expected distribution for that specific service or RPC. This is used to compute system utilization, and the actual latency distribution is also saved to a metrics database for future tuning. Their application communicates the full set of utilizations back to Envoy using the open request cost aggregation specification via a side channel. So we're standing on the shoulders of giants, and we continue to share our advancements through blog posts and presentations to lift the whole community. So that's how we handle traffic spikes through automated prioritized load shedding. I've got about 5 minutes for questions.
So can you share, does it work? Yeah. Can you share more about the exact signals that you're using for load shedding? You mentioned CPU utilization, latency.
Like, yeah, it's different for different systems. All systems are using CPU utilization and also checking for queuing on the CPU. So basically you can look at your load factor. The other thing that's working really well for us is looking at our latency distribution. So when you start seeing like P90 latencies go up, you need to start increasing your utilization. The question is, how do you actually get that tuned? So something that works really well is maybe taking like a P99, and if you see like a P20 cross your P99, then you're in that real bad load situation. Something we do have the capability with this is actually tracking multiple points in latency distribution. This gives us a little bit more tunable for the systems that are harder to tune, but most systems don't need it. We've been pretty good with tracking only 1 point in latency distribution, assuming that we are doing on a per RPC level. Previously, we tried doing 1 endpoint on latency distribution on a per service level, and the problem is you have multimodal latencies, and then you can't respond to it. So that's why it's really important that you can actually get either unimodal latencies or track multiple points in your latency distribution.
How do you merge percentile data across multiple nodes without sending all the like latency data every single time, like for every single request? If you only need a sample.
Yeah, we're using our Spectator library, which is open source, and also the Atlas time series database, which is also open source. It's bucketing the percentiles and then estimating it on the back end. So it's just applying buckets and aggregating it. So they're not strict percentiles, but they're close enough.
Do you use the same signals for load shedding, load balancing, and auto scaling, or do you use somewhat different, like, targets? So basically, like, if you see, like, a node, a pod, like, a unit of compute, load shedding, do you have, like, the load balancing on the same signal, steer away traffic from it at the same time, or do you use, like, an auto scale also at the same time, or do you not combine those two, all three?
It depends. So if you see a spike request going to a system, we're going to auto scale because we know we need any more. Also, if we see a spike in CPU, we will also tend to auto scale because it's easy to add CPU. If you see a spike in latency, auto scaling is not an obvious decision because you don't actually know what resource you're short on, and auto scaling might actually make your problem worse. So we auto scale on some of the signals that we use for load shedding, but not all of them. As far as load balancing, we are using relatively simple client-side load balancing, so we're not feeding these signals back into load balancing right now. Right.
So yeah, thanks for the talk. I noticed that there's a feedback loop based on the OCA protocol. I'm kind of curious, is this system built under the assumption that, over some stable period of time, the latency of a gRPC method is also kind of stable. So then this feedback loop is also kind of stable. So, and you don't have to frequently update your latency statistics to the clients. Is that the assumption?
Yeah, so early on in building the system, I said that I really shy at taking more controls engineering classes, so I would be able to have better knowledge of these feedback loops. We're aware of the feedback loops, and currently we're just manually controlling for them. We're doing that by not using full sampling. We're actually picking known good periods where we have expected latency distributions. That's helping to mitigate the feedback loop. So basically, we measure the latencies when we're not doing load shedding.
Okay, but I think still this feedback loop is effective only if the latency distribution is relatively stable, right, over a certain period of time. Right? If they change a lot, then yeah, I guess.
Yeah, so we need to tune the system frequently, especially if the RPC latencies are changing. Right now, we're doing it every few weeks. We can move that up as needed because it's fully automated.
Got it, thanks.
I'm curious. Instead of you've described a system where you're sort of doing a bunch of analysis. You have these jobs that run that sort of test the system and then write this sort of static configuration. Well, static in the sense of once it's generated, it's that's what it is. Why is that better than having the system react a bit more dynamically to what's actually going on with the traffic? Right. You could imagine having the client check the error rate and the latency of requests going to backends and sort of reacting a bit more dynamically.
Yeah, so the challenge we ran into with allowing it to be completely dynamic is if a client comes up with a blank memory, it doesn't know if it's learning from a system in a good state or learning from a system in a bad state, and that made it really difficult for us to operate. So that's why we liked baking in the actual tuning parameters that we're using, because we know they should work, we know they should be good, and we know that they're from a good state system. Trying to make the clients do it dynamically, we have that with our gradient algorithm in the open source library, and it was just tough. All right, I think we're at time, but I will be in the hallway if anybody wants to ask more questions.